I have a question. So in this talk, you discuss basically a closed system, and you're looking to optimize throughput.
Right.
Do you expect that the type of finding in terms the way you compute the optimal batch size would be at all similar for an open system where you're trying to minimize response time or mean response time?
We actually looked at open formulation with respect to throughput, but the results were pretty different. And although minimizing response time is somewhat similar, somewhat equivalent to maximizing throughput, but we did it specifically from that using that objective function. But if you take the same objective function at like optimizing the throughput, then it's quite different. We tried that first.
That's really interesting. Can you explain how it's different?
That's different because in the open system, first of all, you do not have the constraint that number of jobs always stays the same, and then there is also a constraint here that one client cannot fire another query until it gets the response back. So it gets the response back, and then it waits for an exponential time, and then only it can fire a new query. So there is an explicit dependence between service and arrival, I would say, and that's why it's inherently different from an open system.
Sure, that makes sense. So what I'm asking is, can you explain how that impacts the optimal batch size? And it's possible that for throughput in an open system, it actually ends up degenerating, but I haven't. You're the expert, so yeah, can you comment on that? Like, how the optimal batch size changes going from closed to open?
Okay, so you mean the rate of change, or?
So here's what I mean. If to optimize throughput in the closed system, your paper does this. You come up with some answer. And you said you've also looked at optimizing throughput in an open system. Mm-hmm. And so you get these two numbers, K closed and K open. And I'm wondering, how do K closed and K open compare? Does that question make sense?
Yes. Yes. So I think, it's just a guess. I think in case of open system, you will not have any trivial optimum, because as you go on increasing your batch size, you can simply get something more, because in the open system, I would assume if you can. I think it will also depend on your arrival rate. In case of open system, if you can just scale the arrival rate with your batch size, then you can practically achieve very high throughput. So it's unbounded if you can scale your arrival rate. But
that's
you cannot really do that. Sorry.
I see. So basically, in the open system, the throughput question really isn't interesting.
Yes. Yeah.
Which is why you'd have to consider response time or something. Okay, great. Very interesting talk. Thank you.
You're welcome.
Okay, so we have a question from Slack from Mariam. Do you want to answer this yourself, or?
Yeah. Let me take a look. The right job has preemptive priority.
Also, Line, she can also ask the question directly. Right.
Sure. Hello, thank you for the great talk, Sounak. I was wondering about the case where you're considering two types of jobs, where the right jobs have preemptive priority. I didn't quite get how does the batching and the preemption work together. Is the batcher batching the same type of jobs together? And if not, then how does the server decide how to give the priorities based on, or the preemption basically? How does that work?
Yeah. So basically, you do not have any preemption or any ordering in the batcher, because you only batch jobs of similar type together. So that's one assumption.
So batches of the similar type are batched together, then that will change the assumption for, because if I remember correctly, you made a simplification in the Minfield analysis, where you said that, okay, there is no overhead. Basically the number of active jobs and the number of batches are in this. So I don't remember it correctly, but there was some specification that kind of dependent on the fact that when we have there are only K1 jobs in the batcher, and as soon as the Ks come in, then the batch is released. And now this changes somehow. How does it?
Yes, it does change. So basically, when you have K-1 of one type, and and then another job comes in from the similar type, then only it goes out of the batching section.
Oh, I see.
Otherwise,
so you use two types. Okay.
Yeah. Otherwise, you have to keep track of how many you have from the other type. So in your state space description, that also comes in. So it's not as simple, but still it works out somehow.
Okay. Thank you very much.
You're welcome.
Any other questions? So I have a quick one, Sounak. So you mentioned the service time could depend on the batch size. What's the particular, specific assumption? Do you assume it's linear or it's convex, or any assumption on mu of k?
Yeah. So basically, you only need it in the end when you do the optimization. So we assume that it can be of three forms. For example, linear, logarithmic, and power. But for the theory to be valid, you do not need that beforehand. But when you do the optimization explicitly, then you have to estimate this. And in our experiment setup, it came out to be linear, but we tried tried three of them basically, as said, linear, logarithmic, and power. And we took the one which fit to the data most closely, and that was linear, as said.
So how does that assumption change the batch size? So say like when you change from linear to power, how would the batch size change accordingly? Have you looked at that?
So basically, in that case, we would restrict our what should I say? The speed up function only to be power. But now what we did, we actually restricted it to a bigger class, so it could be linear, logarithmic, and power, all three of them. We try. It's not that we're trying them separately. We try all of them together, and we just pick the best from this entire class. And one set of linear parameters did the best job. That's why we picked it. But if we restrict the class to a power setup, then it's probably going to be a maybe less good estimate, but we will certainly end up with a different kind of estimate. But we did not try that specifically. But I would assume that would be a worse estimate. Only if we enlarge the class of speed of functions, then we could possibly end up with a better estimate.
Thank you. Okay. So any other questions? I think we have. With time-wise, we're okay, but okay. So let's move on. Thank you, Sounak, and then